Okay, hello everybody, and welcome to today's webinar, Enhancing Aluminum Castings for Structural Applications. My name is Jim Beckwith, contrary to what it says on your screen. I work with the American Foundry Society in conjunction with its Metal Casting Design and Purchasing publication, and I'm sure you're all familiar with that one. A couple of housekeeping items about today's webinar. I encourage you to submit questions throughout the webinar as they occur to you. Please feel free to utilize the question button on your dashboard. If you can't locate the question button, we can always do that through chat, but we're trying to reserve chat for other things if at all possible. I will be saving and compiling the questions as they come through, and we will be addressing those in the Q&A session at the end of the presentation. One other housekeeping note: if you are using a telephone to call in for your audio, please mute yourself on the back end to ensure that the sounds in the background don't bleed through into the presentation. Now, without further ado, I would like to bring in our presenter, Mr. David Weiss. David is the Vice President of Engineering and R&D for ECK Industries, ECK Industries Incorporated. He is responsible for development and application of high-performance alloys and casting concepts for the foundry and their customers. Weiss serves on the editorial board of the International Journal of Metal Casting and is a member of the Board of Directors of the American Foundry Society. He was the recipient of the AFS Award of Scientific Merit in 2012 for technical innovations in light metal casting. So without further ado, here's Dave.
Okay. Yeah.
Thank you, Jim. And thanks everybody for joining me this morning to have a discussion about what looks to be the future of aluminum castings for structural applications. And I'm going to talk about a number of different areas that have been research activities either here at ECK Industries or in conjunction with AFS on a number of AFS programs. And so I want to talk about the 356 alloy modifications, ablation, something about CastDecantCast. I'm going to talk about 200 series alloys, temperature-resistant aluminum alloys, casting wrought alloy compositions, and then finally some of the more recent and speculative work that we've been working on with aluminum nanocomposites. 356 is kind of the original structural alloy. It is the most popular aluminum casting alloy. It has moderate strength. It has excellent castability and therefore reliability out of the casting process. And generically, it's an aluminum silicon magnesium alloy. And the silicon is important in one aspect of strength because it reacts with mag to form magsilicide, which is an important strengthening compound in aluminum alloy. From the foundryman's perspective, it improves fluidity, reduces the tendency to hot tear, shrinkage during solidification. It reduces the CTE of the final product. And both 356 and 357 alloys are specified in silicon ranges of around 7% or so. Most of the silicon that's in the alloy is in there for the foundryman. Silicon has an influence on fluidity, although not as much as you would think in molten alloys. When you get above the eutectic point, it becomes more important. But you can pour alloys with low amounts of silicon fairly easily from a filling out of the casting standpoint. We started on this work because customers, of course, always want higher elongations at given strength levels. And so one of the ways that we thought it was possible to do that was to reduce silicon level. Silicon, in general, reduces ductility. and you get excess silicon in the grain boundary, and it makes machining a little bit more difficult than alloys that don't contain silicon. So what we did is we went back to some old work that we had done as far as making clean aluminum alloys, and this happens to be a fairly dirty aluminum 356. And when you get alloys that have a lot of oxide films in, the material will tend to fracture at the oxide films, and that will become your failure point. But when you go and you produce very, very clean aluminum that are free of oxide films, there's a ceiling to the mechanical properties that you can get, because what happens is the material begins to fracture at the silicon that's added to the alloy. So if you take some of the silicon out of the alloy, as theory predicts, you do not change either the tensile or the yield strength of the materials, because you need actually less than 1% silicon to combine with the magnesium. But what happens is you get a big improvement in elongation. As a matter of fact, typically elongation doubles as you move silicon from 7% to 4%. And people like that ductility for a number of reasons. One of the big reasons that they like it is there will be an improvement likely in fatigue performance. It works in 357 as well, that as you decrease the amount of silicon in the alloy, you increase, again, elongation, but not as big of a percentage as you do in 356. And so just a couple pictures of the structure. This is with 7% silicon, and this is with 4% silicon, and you can clearly see the difference in structure with less silicon. And where that really becomes important is in fatigue life improvement. Here we're looking at fully reversed fatigue life at 16 KSI. And comparing 4% silicon versus 7% silicon. And there's a couple of things to note here. First of all, the fatigue life at 16 KSI is about triple using the 4% silicon compared to the 7% silicon. And as well, there is much less variability in the material, and that variability is because of things like silicon segregation that you get at higher levels of silicon. So this is one way to enhance the performance of an alloy that is really pretty good by decreasing the amount of silicon to improve its ductility, its fracture toughness, and its fatigue strength. There's other ways to change that silicon morphology as well, and one of those is a process called ablation. I'm sure some of you are familiar with the ablation process, but in ablation, what you're doing is you are taking an inorganic mold binder and binding the sand together, pouring metal, and immediately ablating the sand away, giving you very, very high solidification rates in the casting. And this all happens fairly quickly, and you can see it. This is an earlier version of the process showing the ablation casting process. And so you end up with a casting that is fully solidified at about water temperature when the material in the riser sleeve is actually still molten. So you get very, very fast cooling rates, typically 25 to 50 times faster than you get in a permanent mold casting. And when you look at a standard 356 alloy using that process versus a slowly solidified sand casting process, you can see that the silicon morphology has changed so much that that silicon is almost indistinguishable in the structure. And this leads to a lot of the same benefits that you would get with the lower silicon alloy, for example. Higher fatigue strength, significantly higher elongation. This process has been around now for a number of years. It is beginning to go into production as a way to make structural castings, and it is likely to be very very successful. I want to talk about a process that we've been working on here for a number of years, which is called the CastDecantCast process, also called co-casting or various other terms. And the CDC process can be used to produce components from two different alloys. Casting is filled with alloy A, which is partially decanted and then filled with alloy B, alternatively filled with alloy A and alloy B at the same time. You know, from a design standpoint, oftentimes customers ask for different mechanical properties in different areas of the castings, and either to improve machinability in certain areas, for a number of reasons actually, which I think I talk about in this slide. So we've been working on it in order to introduce a secondary alloy to improve weldability to other structure. For example, if we use 206 and it gets welded into a body structure somewhere in 6061, it's very difficult to weld 6061 to 206. So what you can do is you can have an intermediate alloy like a 355 in the welding zone in order to improve that. It also can be used to increase strength in one area of the casting by introducing a stronger type of alloy, to improve the corrosion performance of a system by adding some material to the surface, or improve stiffness by locally using a composite material. And some of that type of application is in production here at Eck Industries. So this is one aspect of it. This is looking at like a low pressure CDC system where you fill a casting with or a mold cavity with one alloy. You partially drain that alloy and then fill it again with a secondary type of alloy. And here's an example, and this is the as-cast product. This is a 206. Traditionally CDC cast with a 355 alloy, and of course you see that interface there, and that interface would be considered a bad thing, and it is indeed, because you're not going to get any kind of good load transfer across that interface. However, at least in this alloy system, when you heat treat the material, you get diffusion of the alloys together at the heat treat temperature, which forms a true metallurgical bond in the material and allows for load transfer and all of those things which are important in trying to use multiple alloy systems for actual castings. I gave a couple years ago, I think now, I gave a separate webinar on 200 series alloys. We pour a tremendous amount of 200 series alloys. We pour them every day in hundreds of different part numbers in our facility. 200 series alloys are the strongest and toughest aluminum alloys available, at least some of them in some of the tempers. And they're heat treatable to either a high toughness or a high strength type of condition. They have good fatigue properties. 206 in the T4 condition has probably the best fatigue properties of any cast aluminum alloy. There tend to be aluminum copper alloys, so they have good to excellent high temperature strength depending upon the material you're using, and they're affordable. They're, I usually say they're about 25 cents a pound more expensive from an alloy cost standpoint versus an alloy like a 356, so they're affordable. And these alloys have a reputation of being difficult to cast, but understanding how to feed alloys that are difficult to feed, setting up proper thermal gradients, and now with all the software tools that we have to cast difficult to cast alloys, they become much, much easier to produce castings from without having to go through a lot of iterations as far as learning how to do it. And so if you look at the mechanical properties of these alloys in the T4 condition, and these are typical to minimum type of mechanical properties. You know, 206 in the T4 condition, you get 50 KSI, tensile, and 30,000 yield, and about 10% elongation, which is pretty good. In the T7 condition, which is exactly the same material except heat treated a little differently, you get higher yield strengths and lower elongations. And so, you know, when you compare that to 300 series alloys, gray iron or ductile iron, some of these alloys compare very, very favorably to those, and so have become a bit of the focus alloys to making structural castings or conversions from other materials into aluminum structural castings. This is a great example. This is a part that's been in production continuously now, approaching 30 years. This is the final drive cover for the Bradley fighting vehicle. We also make the final drive housing for the Bradley vehicle. And this, when it all started, was a conversion from ductile iron, and 110 pounds of weight per part saved on this particular component. Been in continuous production, has really literally and figuratively been bulletproof, because these are used in combat conditions all the time. And the new Bradley recapitalization is not moving away from this alloy, even though the vehicle has doubled in weight. And you know, we'll stay with this material because of its outstanding performance in the field. This is a more recent weight reduction success story. This is a conversion from ductile iron into a 206 aluminum. This slide is used by permission of our customer, and this is a fairly large knuckle. It's for a military vehicle. And this particular part offered a weight savings of about 60 pounds an axle, which is really, really significant in the on military vehicles. It reduces weight, therefore fuel cost is less, and fuel cost is very, very high in military applications. This is a great cost reduction success story, even though you wouldn't think it. This is a gun port shield, and this is a conversion from a 70-75 hog out to a 201 casting that is subsequently hot isostatically pressed. And it's like, you would think that is going to be very expensive, but it is, because 201 is the silver containing 200 series alloy. And so that goes for $6 or $7 a pound, and to that you have to add the cost of hipping. But it resulted in almost a 50% cost savings from the 70-75 hog out, where they only used about 14% of the material that was in the billet in order to produce the product. So this is both a structural success as well as in this application, a big cost reduction for the customer. We use a slightly different kind of 200 series alloy, 242, typically to produce cylinder heads, and you can see that you have very thin type of fins on these, and we use a number of special techniques to ensure that we can make them, but but it's clear that you can pour almost any casting and make a good casting in 200 series alloys, as long as you follow the rules and you use the proper techniques to be able to use them. One of the reasons that 200 series alloys are not used widely, for example, in automotive applications, is because they have a reputation for hot tearing, particularly in metal molds, and that is indeed true. Again, we're using the latest techniques to understand 200 series alloys in permanent mold castings. As a matter of fact, at the AFS Casting Congress this year, there'll be a panel presentation on developing 206 in permanent mold, and this work was very successful in that it told us that the key to being able to produce permanent mold castings in this alloy is temperature control of the tooling, being able to get it consistently hot enough to avoid the stresses that create hot tearing, and not so hot, of course, that you have some sort of mechanical cracking during ejection. So this is a very successful program, and to learn more about it, you can either contact me or, better yet, come to Casting Congress and hear the whole presentation on it. 200 series alloys have good high temperature applications. One of the ones that we pour all the time is a 224. It's an aluminum, copper, zirconium, vanadium alloy, and you can see in the T7 properties after 1,000 hours exposure at 500 degrees Fahrenheit, which is really quite high for aluminum alloys. If you test it at 500 degrees Fahrenheit, you still have good tensile and yield strength. If you test it at room temperature, you actually get an enhancement of strength after exposure to that kind of temperature. So it's a extraordinarily good alloy for high temperature applications. There's a lot of work going on in high temperature aluminum alloys. Again, at Casting Congress in spring, there's a number of good papers that are going to be presented by a number of different companies about high temperature aluminum alloys, either enhancements to the 300 series or enhancements to the 200 series. This is some work that we're just writing a final report on aluminum copper scandium alloys that are very, very stable at 250 degrees C. Right now the alloys are a little bit expensive because of the cost of the scandium, but nonetheless we've already moved into commercial production on a couple parts on these alloys where they are exposed to high temperatures for very, very long periods of time. I'm going to talk in general about casting of wrought alloy chemistries. We've done a bunch of work on that, and we've kind of worked backwards, understanding that a lot of customers, are interested in having properties that are close to the properties of wrought alloys. The wrought alloy chemistries are different than most of the cast alloys, and in many cases it involves very low levels of silicon, which we talked about in the low silicon 356 section. So this program was a program that was through the American Foundry Society, and really looking at 7075 alloy as part of an Achieving Lightweight Casting Solutions program. The project sponsor was Benet Labs, and as I said, managed through the American Foundry Society. In an alloy like 7075, it turns out that the mechanical properties are controlled by dendritic iron and silicon phases. That's not particularly surprising, and when you have those phases, your elongation goes down if they're not widely dispersed and separated. In this work, we modified the 7075 chemistry a little bit to make it a little cleaner. Took out some of the iron to make the iron in line with an alloy like A356 alloys, and did some other slight modifications to the chemistry. But it fully meets all the chemistry requirements of the raw 7075 material. And what we did is we made a number of test castings and then some real castings as part of the program. And you can see for this material in the T6 temper, in a well chilled type of application, we're getting tensile strengths near 80,000 psi, and yield strengths in the low 70s, along with very, very good elongation. This is the kind of material that I would hesitate to say you can make any casting from, but you can certainly make some castings from this material. Things like simpler shapes like brake calipers, perhaps, or some of the products that are hogged out of 7075 sheet currently. It's not as versatile an alloy as a 206 alloy, but nonetheless it is going to have commercial applications at those strength levels. I'm going to talk a bit about a program that is unofficially or officially from the government standpoint ending. We did work along with the University of Wisconsin-Madison, which was originally scheduled to be a 5-year program and was cut to 3 years because of funding concerns on aluminum-based metal matrix nanocomposites. The ability to do this it's very difficult. There's a lot of different phases to get nanoparticles into aluminum alloys the way so that they function as strengthening agents. And so the reason we did it, of course, is we were looking for properties better than the base alloys. And the challenge is really nanoparticle distribution control. Typically, when you get nanoparticles into the melt, which is difficult all by itself, they tend to cluster like in picture number 1. What you really want to do is get something like picture number 2, because that'll give you your maximum strength in the alloy. However, oftentimes when you get them into the melt successfully, you end up with picture number 3, which doesn't give you much strength. However, it gives you some interesting castability controls by getting those nanoparticles into the interface. So this work actually started with an American Foundry Society seed grant to look in very small volumes what you could do as far as getting nanoparticles into a melt. And that program worked around how do you decluster material once you get into the melt, and a very reliable way to decluster clusters of nanoparticles is ultrasonic processing. And indeed, this is very successful. I'll show you pictures of how we get ultrasonic processing through a larger melt. But this is a reliable way to break up the clusters, and if you can break up the clusters, you're part of the way to making an enhanced, a strengthened nano-reinforced casting. And this is some of the work that came out of that original American Foundry Society sponsored program, where in small batches, and we're talking batch sizes of a pound or two, that they were able to demonstrate a doubling of mechanical properties in the A356 using a 1 weight percent silicon carbide nanoparticle. And these results were the basis for a larger program sponsored by the National Institute of Standards in order to attempt to scale up this technology into batches that, as foundry people, we would actually be interested in doing and customers would be interested in buying. So there's a lot of issues with volume production of metal matrix nanocomposites. You got to find the right matrix alloy. You got to find the right particles for the alloy of choice, because some particles react with the alloy. You've got to get particles into the melt, which is the most difficult part of this. You have to distribute or decluster the particles in the melt, which you can reliably do with ultrasonic processing currently. And then it seems that the processing parameters for any given alloy particle combination are a little bit different. And so it's important to realize those distinctions and move accordingly. When you're doing ultrasonic processing, you typically ultrasonic process only in a fairly small area, because the ultrasonic waves get attenuated in liquid aluminum fairly quickly. And for those of you who are having a coffee, about the most effective size that you can ultrasonically process is about the size of a coffee cup. Well, the question is, how do you get the material into the ultrasonic zone? And for that, we developed a pump that pumped the metal through and out of the ultrasonic zone to allow for ultrasonic processing of a whole batch of material. That's what it looks like in real life. The ultrasonic probe is in a smaller container that the material is pumped to. So it gets pumped into that area and then pumped through it. And in that pumping operation, you're able to distribute or decluster the nanoparticles and make them useful. The biggest problem, as I said, was getting particles into the melt, and in this program we did a number of different things in order to be able to do that. Nanoparticles have large specific surface area, they have a high energy, and you're fighting against the surface tension of the melt. So one of the first things that we did is we actually tried to encapsulate them into a multi-part squeeze casting that we would then introduce into the melt. We had mixed success with that. The puck on the left has fully wetted nanoparticles. The second one is completely unwetted, and the two on the right are partially wetted. There was also an issue with being able to melt these evenly in the melt, because the outside layer where there were no nanoparticles melted very easily, and the percolation of aluminum through the very dense particle bed was very slow, so it took a long time to melt these. But you can start with these pucks, and you can melt them along with whatever alloy of choice you're doing. Here we do it in a, this happens to be 206, and this is a 25 kilogram furnace, and then we melt and pour off castings. This is another attempt where we actually try to extrude particles into a cylinder and really create kind of grain refining rod that we could melt. This is a much more successful way to bring particles into the melt, although you have to be very careful when you're extruding, because hard nano particles can can create problems with your extrusion tooling over time. But it was very successful. This is these are particles before ultrasonic processing that were done with a multi-pass extrusion, and you can see some fairly good distribution. And when this type of melt is ultrasonically processed, you do the remaining declustering, and you can successfully pour castings, as you see here. One of the problems with nanomaterials is that you get particle pushing during solidification. It likes to push to the grain boundaries in most alloys, and one of the kind of side trips that we did on this program was to look at, and here's a picture of it. This is kind of the particle dispersion that occurs after solidification, where you're forming a network of particles around the grain boundary. And however, if you take materials like that and do some solid state stirring, like friction stir welding, which has become a more and more common process, you can completely disperse those particles throughout the structure. And so it suggests that this may be a good way for surface strengthening, engineering fatigue resistance into fatigue-prone areas of castings, and other potential kind of applications. One of the other really interesting applications in nanoparticles is in, like, the aluminum tin or aluminum bismuth series of alloys. I mean, you know, tin and bismuth have limited solubility, they have low melting points, and so they tend to form globules in these alloys. That's actually an advantage when you're using nanoparticles, because the nanoparticles tend to self-assemble at the interfaces between, in this case, the bismuth and the aluminum, and then what you get is you get wonderful distribution of some of these mainly immiscible alloys through the use of nanoparticles. This is the most interesting picture that I'm going to present today. This is some material that was produced where we altered the charge of the particles versus the aluminum alloy, and this again is before ultrasonic dispersion. And so we ended up with these watermelon type of clusters in the alloy that have almost perfectly dispersed nanoparticles into them. And if you do a micro hardness on the areas where we see these footballs, and you do the typical relationship between hardness and yield strength, the indicated hardness would indicate a yield strength of about 175 KSI in that area of the part. Now, to get this completely distributed through the melt, that's another problem, and has not been done consistently yet in these materials. One of the things that we didn't expect is that when you add nanoparticles to aluminum, it completely changes its hot tear resistance. So for alloys like 7075 or alloys like 206 or 201, where there is some tendency to hot tearing, you can actually use those particles at the grain boundary not as a strengthening mechanism, but as a way to prevent hot tearing. And we went back and forth about you know, was the ultrasonic processing doing something all by itself, or were the particle additions doing something? And you can see grain sizes in 206 material, and they are not the smallest grain sizes with the addition of in this case alumina nanoparticles. They're not as small as we do traditionally when we add boron type of grain refiners to it. And so what we did is we did a typical hot tearing type of test and put a numerical factor on the hot tearing tendency of the material, and when you do that with alumina nanoparticles in particular, grains were refined, but not as refined as with conventional grain refiner. However, hot tearing susceptibility was significantly enhanced, and that is due to the effect of the addition of nanoparticles. So if you get nanoparticles into the melt, get them distributed, at least this system, alumina in 206, most of those particles will go to the grain boundary and almost completely arrest the tendency of an alloy like 206 to hot tear. You get material which is has about the same hot tear resistance as 356, which, as most of you know, is really pretty good. So, kind of in conclusion, that there's a lot of alloy options that can be explored for high-strength structural castings. A lot of those are available today. The lower silicon materials, certainly the 200 series alloys are available routinely. There are some of these advancements which need a little bit more work in order to improve their reliability, like CDC and nanoparticle reinforced aluminum, but they promise huge strength improvements in aluminum casting alloys in the near future. So we're optimistic about it and continue to work on it, and we'll have many applications, we think, in the near future. For anybody who is interested in sending me any specific questions or wants additional information on any part of my presentation, I'd be glad to answer your emails. And this is where I am and who I am. And at this point, I guess we turn it over for questions. That's the end of my presentation.
Yeah, thank you, Dave. Yeah, we do have a few questions that have trickled in for you, and feel free to keep them coming to the audience. We are targeting to get you out of here by 11 o'clock Central Time here in the next 15 minutes. So, but we can take a few questions before we go. The first question I have is just sort of a point of clarification. We had the question specifically about the nanocomposite strength chart. Just wanted some clarification on the temp numbers. So what 700C, 600C, what all those meant.
Okay. Can I still go back and people can see that?
Yeah, yeah.
Okay, here we go. Yeah, let me do a little bit more detail on that. So in the early work that was sponsored by the American Foundry Society, we did a lot of work as far as optimizing the processing parameters. And one of the things that we found was important is at both the ultrasonic processing power as well as what temperature the material was processed at. And as you can see, you actually have better mechanical properties at processing temperatures that are lower. There is an optimum processing temperature, which actually is between the lower bounds and the upper bounds of what we work with. So we're not sure really if that is alloy specific, if it changes with different alloys, and exactly what the mechanism is that that creates that. But we do see differences in dispersion depending upon what temperature we are operating the ultrasonic probe at.
All right. I have another question that came in. Can you elaborate on best practices for using copper chills?
That's a good question, because copper chills are they have some good attributes. Typically, I'm not sure that I know what the best practice is. I'll be glad to tell you what we do. We typically take a copper chill and make sure it's clean. Generally, we do some light blasting on it and then cover it with a zircon wash before we use it. Not sure if that's the best practice or not, but that's what we do.
All right, a couple other questions here. In low Si alloys, since the fluidity is low, how do we prevent cold shut and shrinkage?
There is, in our own experiments, in the ranges that we talked about, which was between 4 and 7% silicon, I doubt in a typical casting, something with let's say a 4 to 6 millimeter wall thickness, that you're going to detect much difference in fluidity. We certainly haven't doing it here, and of course, we're pouring some materials like 206, which have no silicon in, and so maybe we're more used to it, but we don't see it as a problem in normal wall thickness types of castings. It will probably have some influence on very thin wall castings that are, for example, 3 millimeters. You would expect that there would be greater problems with that, and you're going to need to adjust your gating system. As far as shrinkage, I think that's the easier one to approach. What you look at doing is you establish a more aggressive thermal gradient through mold cooling and slightly larger riser sizes with the lower silicon material. But if you are at 4%, those are smaller problems than if you tried to do something like at 1%. Which is kind of why we stopped. We wanted to make sure that the material remained friendly to the foundry, at the same time as trying to enhance the properties.
All right, we have a couple of questions regarding the castability of A356 when the Si is reduced. Is that something you can address?
Yeah, I think what I did is I pulled out my history slide, from this presentation, because I didn't want to spend time talking about history. But if you look at how the aluminum silicon alloys developed, they developed really as aluminum 5% silicon alloys, which at the time people thought were adequate in order to have good castability in material, and they were there for the longest time. The addition of silicon to the alloys was done because foundrymen wanted it done in order to further improve the castability. With that work that was done around World War II, however, it doesn't take into effect all of the improvements that we've made in the casting process. For example, the cleaner your metal is, the more fluid it is, and so a 4% silicon alloy is about as fluid as a dirty 7% silicon alloy would be. So we have done all these things to try to make better castings, and all of those have lessened the need for us to use that silicon as a crutch. I would, if you would assess castability of 356 as excellent, I would say 4% 356 is good. So there are some adjustments, but they don't need to be that big, and I'm sure everybody who pours 356 can find their way around those.
All right, and we have a question about aluminum and copper alloys. How is the corrosion resistance? How much corrosion resistance would we lose with respect to the strength gain?
You lose the users of these materials, and 206 or aluminum copper alloys, they self-passivate just like most aluminum alloys do. You end up with a layer of aluminum oxide on the surface. Our customers, for example, the people who produce the Bradleys, the transmission components that we've used in the M1, will tell you that from a practical standpoint, in the tempers that we use because heat treat will have effect on corrosion resistance, but in either the T4 or the T7 temper, there is not a corrosion issue on parts. And keep in mind that these parts have been used since the beginning on the Bradley, very early in the M1 program, and are in many, many commercial applications. Those people who are concerned about corrosion, they may put an allodyne coating on, but then again, they may put an allodyne coating on 356 as well to protect against corrosion. From a practical standpoint, in either the T4 or the T7 temper, these alloys do not have a corrosion problem.
All right, well, that appears to be all we have for today, so we'd like to thank everybody for attending today. Those of you who have asked about the possibility of the presentation being archived online, it will be, and you'll receive details about this via email. In conclusion, I'd like to thank David Weiss and Eck Industries for the valuable presentation. And thank you again for attending today, and have a great day.
Okay.